So, let's begin. What is the name of the Grinch's dog? Do you know who the Grinch is? You have a hard enough time hearing me in English. Never mind with musical. You don't know who the Grinch is, Junior? No?
They won't let me answer on their own. If I put this in and it says it's wrong,
What?
I watched this the other day.
Buster was never enough right. It's not sensible.
You remember Buster?
I do remember Buster.
Okay, so yeah, you should have got, everyone got it. Yes, it's Max. And the reason that it's a nice way for me to sort of introduce this kind of thing, and it's just a visual more than anything. In the movie, the original cartoon movie, the Grinch ties the little reindeer thing to the back of his head, right? And then they go down the hill, and the sled goes faster than Max does, and he ends up going like backwards or underneath, right? Coming around, right? So I always like to talk about the acceleration because the sled is speeding up as it goes. Johnny, you need to pay attention to me. Merman's not explaining it to you. Okay? I don't want to have to come by and explain all this to you personally. I'm speaking to you right now. Okay, so, and if you choose to write these down, you can. If you want to just print this out at home or later or whatever, you do what you need to do to understand acceleration. Okay? Acceleration is, like velocity, a what kind of quantity? And I just gave you the answer.
Because it showed a bunch of green on the left and a few reds on the right.
Maybe.
Or maybe it was the other way.
Maybe it was the other way. Remember, it's backwards on the screen, right? Like when I look at it, it's backwards.
Oh.
Acceleration, like velocity, is what kind of quantity? It's either a vector or a scalar. What's the difference? Vectors have a direction. A or B, Olivia? Correct answer is? Acceleration is a vector. It does pretty much, doesn't it? Right? There's still a few people that didn't get it right. Acceleration is a vector. It has a direction. It could be positive, could be negative, could be like north, south, east, or west, or any of those combinations too. Right?
What's the next one?
I think I did, yeah. I got to get better at that. It can be positive, acceleration. Positive direction could be left, right, up, or down.
Could be any of them.
Technically, you are incorrect, Cole. Most of the time, though. Conventionally, we assign it to certain directions. So acceleration can be positive, which means, come on.
Is it up?
Come on, Dawson.
Is it up?
Come on. Correction, actually, the answer is B and C.
Okay, there you
B and C. To the right. Gotta have them both. Gotta have them both.
Hey, you can't even answer two.
Yes, you can. Yeah.
Let's go back. Yeah, go back. I got it right. Oh, Zero got it right.
Yeah.
Answer B and C.
Anyone need a Kleenex?
Yeah. I got something that was over here.
That was a trick question, and the rest of us thinks we protested.
Hoo-hoo.
Protest. Well, I know how to answer this one.
Yeah, you better get this one right.
It could be two of them. Just a hint.
By the way, you can answer more than one answer.
Oh,
well, I know that.
It can be negative, like your attitude right now. Left, right, up, and or down. Acceleration.
Yeah, let's see about it.
A and D, left and down, right? Okay, now, I will say this is more of a question to generate a conversation than me caring whether you get it right or wrong. So don't freak out. But the question is, does deceleration always mean slowing down?
Yeah, no.
Y or N?
Oh, crap. Oh, I pressed B. Oh.
Well, B is N, I think. Y or N?
Oh boy.
Yeah. Because you can be accelerating to a constant speed.
Yeah, but you still slow down to that constant speed.
Does everyone know where the Y and N buttons are on their clickers? Come on, Zane. Make a choice.
50-50.
And the correct answer is no.
Right on.
50-50. Okay. Now, the important thing here is not whether you got it right or wrong. The important thing is to understand maybe why. So listen here. Acceleration to the left, which might be negative, is sometimes called deceleration. Okay? So deceleration tends to mean negative acceleration, but negative acceleration doesn't always mean slowing down. Because what if I am already moving to the left? What if my velocity is -5 to the left and my acceleration is -2, a deceleration, if you will, of -2? Well, then that thing's going to do what?
Slower.
Not going to go slower. You're speeding up in the direction that it's going. So in this particular case, this one is actually doing what? Accelerating, speeding up, right? Now, to be fair, I should probably change this question to, does negative acceleration always mean slowing down, right? Here's what I want you to get out of this. I would suggest you not use the word deceleration. Just say positive or negative acceleration. Negative just means to the left, but negative acceleration doesn't necessarily mean slowing down. Zane.
Okay, well, if you looked up deceleration in the dictionary, it wouldn't say speeding up in the negative way. It'd say slowing down.
Probably. Yeah. But my point is, you're right. You're not wrong about that. And again, don't worry about whether you got it right or wrong. You guys got to stop worrying about the marks and the numbers. Worry about learning stuff.
So are you supposed to?
No, Jeff. If you learn stuff, the marks will come. Trust me. When you know things, it's shown up in your mark. If all you do is worry about the mark, then all you're doing is memorizing. You're not worried about learning it.
So are you supposed to add the A to the B?
Sort of. Well, I'm going to talk about acceleration today, right? So I'm going to talk to you about what that really means. You probably don't have a good sense of it just yet. I'm going to be talking about this today. Okay. So here is the definition of acceleration. Now you can choose to write this down if you wish. If you want to just print it out, you can. That's fine too. Here's a formal definition of acceleration. By the way, I handed out some graphs and some stuff there. Kids in the past have cut and pasted them into notes. They've just sort of included it. Maybe they've written on figure 1, figure 2. They've written their notes on the back of it. I don't care what you do. You're all students that have been in school for a while. You figure out what works for you. If doing nothing works for you, okay. But if doing nothing doesn't work for you, then don't do that. Write down what you need to make yourself successful. Acceleration is the time rate of change in velocity. It is a change in velocity. Those are the key terms. A change in velocity, and it is that rate. In other words, how fast does the velocity change? How fast does the velocity change? Okay, so acceleration, time rate of change in velocity. I'm going to pop. Another way to say this that might be helpful for you is how fast an object's velocity is changing. How fast the speed is changing. Or. Right. Well, there's one more sentence after. It's how fast an object's velocity is changing. It's not how fast it's going. It's how fast its speed is changing. And there's a difference. And I even find in grade 12, I still have kids that don't truly understand what acceleration means. Or how fast an object's velocity is either increasing or decreasing. How fast is it changing?
How do you measure that?
I'm going to get to that too.
Okay.
Acceleration.
Do you mean what units is it in?
Like,
Oh. How do you actually measure it? You have to figure out how fast it's going at the start of the interval, how fast it's going at the end of the interval, that difference, how fast it, like
Yeah,
how
but
much
what
it
if
changed.
What if it's like really fast and slowing down really fast?
Well, then you're going to get a varying acceleration, right? You're not going to get a constant acceleration. Trust me, I've been through this lesson a lot, and I know all the sort of checkpoints along the way. If you want, here's another way. Some kid said this to me once, and I wrote it down. How fast you get to how fast you are going. How fast you get to how fast you are going.
How fast you get to the speed you're going.
Right.
Why
How fast
would
you get
he
to the
say it
speed
like
you're going.
that?
I don't know, that's what he said, and I liked it, so I wrote it down. I don't know if it was a he or she, I can't remember.
Oh, yeah.
Must have been quite a few years ago.
It is, yeah. Yeah, that's why I do multiple ways of doing it, right?
You're driving, you're like,
I don't know how many seconds it takes me to get to this speed.
oh, that was my first gear. My first gear took a second before I clocked in on second.
Okay. Everybody good? So, give me a vehicle that gets up to speed really fast.
Brett's truck.
Lamborghini,
Nissan
You
GTR.
forgot Brett's truck.
motorbikes, right?
Right. BMW.
Bugattis, they go from 0
Ultimate
to
Aero.
like 200 kilometers an hour really fast, right? They have good acceleration. Yes, scooters tend to have good acceleration. Give me an example of a vehicle that has low number of
Semi.
acceleration.
We have a lot more ideas for this.
Yeah. Alright, so usually, usually things that are big, right? Tractors, semis, even would you say like rockets that are going to space? Right? They go fast, but they don't go like really quick to start. They go slow and they speed up over a long period of time, right? Even like airplanes taking off start off slow and eventually get going quite fast, right?
Kid squad.
Yeah, trains for sure.
Trains, yeah. Big things, exactly. Okay. All right, so now Brett asked, how do you measure it? So here are 4 possible formulas. You need to pick out the correct one.
Wait, what do you mean we don't?
Okay? Well, I've told you what acceleration is. I said it's how fast the velocity is changing, or it's the time rate of change of velocity. So which of these formulas does that translate to? Cool, take a look and figure it out. Keeping in mind, acceleration is a change in velocity over a change in time.
Oh, well, that was a lot easier when you say it like that.
Oh, but then it's T. That's what delta stands for.
Oh, I screwed up already. I have to slow it down.
Duh.
I said it was in
We do.
Come on, Johnny. Correct answer is? Yep. It is the change in velocity. I heard Dawson say it. That's what delta means, right? Delta V, Cole, means change in velocity divided by change in time. So you take your 2 velocities and you subtract, and you divide that by your change in your times. And usually the initial time is just 0. Usually. Okay? Okay. So here we have the first graph that you guys have on your sheet. So if you want to cut, if you're writing notes on loose leaf, you want to leave a space, you can cut it out, tape it in. If you want to write a note right on the graph, I don't care what you do. They're your notes. I'm not the notes police, but I provided that for you to be able to do that. So in the graph below, this is a position time graph or displacement graph. Position time is a curved line. Now remember, when we did the rolling ball lap just the other day, I have some of yours in, some still need to do that, right? There was the line when it was on the floor. When the ball's on the floor, it was traveling at a. You guys listen? Because you guys, I don't understand how you don't understand that when I teach and you learn.
Bro, I got 100% on the last one. I'm doing pretty all right right now.
I understand. I'm still teaching. I know. Stop worrying about the marks. Worry about learning. Okay. I'm going to explain. Listen, I'm saying, I'm giving you hints. When you did the rolling ball lab and the ball was on the floor, it was traveling at a constant speed, right? When it was actually on the ramp, it was increasing. Okay, so knowing what you know about that, you should be able to get this answer right. And I have to do this too, don't I?
I like when you put the grass slowing down. Increasing.
So in the graph below, the displacement graph is a curved line, meaning that the velocity is A decreasing, B increasing, or C staying the same. Staying the same. The velocity.
Yes. Now I think.
Great on. I'm gonna get it right.
And let's see how you did. Correct answer is B. It is increasing. You should have found a graph like that when you did that lab. How do I know? Would you say the slope is increasing? Here the slope is really flat. There it's steeper. There it's even steeper. There it's even steeper, right? The slope is getting steeper, which means that the velocity is getting increasing, bigger. Right? Moving faster and faster. Okay. Now, this one you're going to have to think. Since the velocity is increasing at a constant rate, the velocity is increasing at a constant rate. It's speeding up by the same amount each time. The velocity graph. Now, this is probably the first time you've ever seen a velocity time graph. These are all graphs of velocity versus time. Velocity versus time. So this is the corresponding position time graph. Since the velocity is increasing at a constant rate, the velocity graph is a what line as shown below? Does the velocity graph look like this? Does it look like this? Or does it look like this? Flat, increasing straight, or decreasing straight? I'm just going to cover this last part up here. This one you're going to have to think about.
Increase.
Yes. The velocity is increasing at a constant rate. This is the position time graph. Which one of these velocity time graphs is the corresponding one? Goes with. Is it A or B or C? I don't know.
Wait, I need that translated.
Increasing means going up, getting bigger.
Decreasing
is getting smaller.
Increasing, it's he already increased.
No, it means in the process of increasing. In the process of getting bigger.
We started fast, like increased by
Okay. The correct answer is B. Correct answer is B. Let's stop and analyze this for a second, right? It says the velocity is increasing, right? Well, that means that as time goes on, as time goes on, the amount of the velocity goes up. And if it's increasing at a constant rate, Ty, what are you doing? You need to listen, man. Put that away. Increasing at a constant rate. It's going up the same amount each time. It's increasing straight. This position time graph goes with this velocity time graph. Okay? The acceleration graph is... Oh, I forgot. Hang on. Let me go back one here. This is something you need to know. Big star. Highlight. Whatever. The BT graph is a graph of the slope of the PT graph. I'll explain it again. The VT graph, the velocity time graph, is a graph of the slope of the PT graph. Okay?
How much?
Let me explain. If every second, I'll let you get that down, the VT graph is a graph of the slope of the PT graph. Here's what I'm talking about. If every second I found the instantaneous slope, how do you find instantaneous slope on a curve? You have to draw the tangent lines, right? So if every second I drew a tangent line and found the slope, the values of those would do what? Getting bigger and bigger and bigger. Now I'm not going to calculate, but let's just say, for argument's sake, that the slope at 1 is 1, and then the slope becomes 2, and then the slope becomes 3, and then the slope becomes 4, and then the slope becomes 5, right? If you were to graph 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, it would go up at a straight line like that, wouldn't it?
Yep.
Okay? Because the slope of the PT graph, or the DT graph, the slope of this position time graph is the velocity. And as you find that many times, it looks like this. That's something you're going to have to know. Okay?
Okay, so if it was just a straight angle, it would be a 5.
Right. Good job, Brett. So Brett's saying, if the position time graph was like this, then which one does that correspond to?
Flat one.
The flat one. How come? Because the slope's not changing, right? Slope is not changing. The value remains the same. Well done.
Right on.
I'm going to come back to that. In fact, well, no, I haven't come back to it yet. I will. Okay, so keep this in mind, this VT graph. Don't start having side conversations, you guys. Jeff, you need to listen. We're learning. Here's our velocity time graph, right? Now, the acceleration graph. This is something that we have not talked about yet. The acceleration graph is a graph of the slope of the velocity time graph. Just as the slope of a position time graph is velocity, the slope of a VT graph is the acceleration. The acceleration graph is a graph of the slope of the velocity time graph. The acceleration graph is a graph of the slope of the velocity time graph. Now, what does our velocity time graph look like? It's straight like this, right? What's the value of the slope? It's constant. It's the same number all the time. Let's say that the slope of this graph is 0.4. What would the acceleration time graph look like then? It would be a flat line at 0.4. Exactly. Okay? This is the corresponding acceleration time graph.
Are all 4 of these graphs?
You need to be here, Cody. You got to go to the bathroom at lunch. You know what? Go, but next day, you got to go at lunch. This is why I have to re-explain things, because you missed little bits and pieces. Go. You got to be in class, you guys, and on time. Okay? This is called uniform accelerated motion. Why is it called uniform? What does uniform mean? The hockey team wears the same uniform, so they all look the same. Uniform motion, uniformly accelerated motion means it's going up by the same amount each time. The same amount. This is called uniformly accelerated motion. So, I think you should draw this little sort of diagram, I guess you could call it. I was going to put it on the board, but then I thought, no, why do I do that? If you have a position PT graph, and you find the slope, then that gives you the VT graph. And then if you find the slope of said VT graph, you end up with a
AT graph.
Exactly.
Yeah. Then you get this one that has the squiggles, I guess.
You can find the slope of the AT graph. What would be the slope of the AT graph? Or what would be the numerical value of the slope of this one?
0?
Yep. But as I said way back at the start, remember I told you, I said every graph slope has a meaning, right? The slope of the PT graph is the VT graph. I need to make myself some room. The slope of the VT graph is the AT acceleration. So what do you think is the slope of the AT graph? It's a word you've heard it, but you've never heard it in this sense. It's called the jerk. If you've ever, and there's actually another name for the next one as well. I don't even remember it, but there's another name for it. You don't need to know that. It's just kind of an interesting side story. If you are taking advanced math next year, and some of you will consider it, the calculus term for taking the slope is called the derivative. If you take the derivative of a PT graph, you get the velocity time graph. If you take the derivative of a VT graph, you get acceleration. If you take the derivative of acceleration, you get the jerk. You can take the derivative as many times as you want. Okay? And Mr. Ray will tell you what a derivative means. Okay. This velocity time graph, and I think you have a picture of it, right, is an example of what is called variable motion or variable acceleration. Now this one here, we said was called, where was it? What that question was it? Oh, wait, here it is here. Uniformly accelerated motion. This is uniform, smooth. This is an example of variable acceleration. The acceleration is not staying the same. The acceleration is not staying the same. Oh, I'm kind of giving the answer.
I hope we all get this one.
Maybe I did that on purpose, Brett.
It is deep. It's deep. What?
First, you better check what kind of graph it is. What kind of graph is it? It's a velocity time graph. What can you tell me about the acceleration?
Sped up. No, it kind of like going faster, it kind of slow down. And then it went.
I want to have a look, see what. Oh yeah.
Does that mean that it went like backwards? Or another place down there?
I'm not gonna answer that question yet because I know what question 10 is. Ty, how about an answer? A, B, or C? This velocity time graph is an example of variable acceleration. Correct answer is A. Well done, you guys. Not constant. The acceleration is not, this person is putting their foot on the gas and taking it off, right? Putting their foot on the gas, taking it off, right? And the velocity goes up and then comes down and goes back up again. Okay. Here's the hardest question of the day. I know, that's why I didn't answer it.
Yeah.
Does this object ever move backwards?
No.
It's yes or no.
Not according
It's just like in court.
Wait,
That's
question,
velocity on the
is
side.
it backwards like at all, or is it like backwards from the start?
Moving to the left.
Oh.
Like if I start here, if this is zero type, okay, and I go like this, right, and I'm over here, and I'm going backwards, but I still got to start.
So you're still going
I'm
backwards.
going backwards, but I haven't got to I started this. Like I don't have to be here to be considered going backwards. I'm just moving.
You just gotta figure out what kind of graph it is.
I screwed up.
It pretty much tells you.
Yeah.
Does this? Yeah, you're right, Brett. Does this object ever move backwards?
Hey.
We just gotta look at
As long as you understand the
Zane, I need an answer. I know. Zone back in. Stay zoned in.
Oh, Jordan. Did you get a 16 today?
It's okay to get it wrong. That means you've thought about it.
I think I screwed up.
No big deal. I'm not recording these marks, you guys. You guys worry so much about marks. Worry about learning. The correct answer is no. It does not move backwards.
When it goes over the x-axis?
How? I'll get to that. Hold that thought. Okay? What is happening? Let me just double check here. What is happening?
I think because he down the velocity, not the...
That's true. What is happening between A and B? It's just slowing down, but still doing what, Olivia? Johnny, listen! Stop playing around!
Still driving.
Still driving which way?
Forward.
Forward. The velocity at all times is in what region? Positive. The velocity is always positive. Positive 1, positive 2, positive 3, positive 4. Then it goes back. Shouldn't say it goes backwards. Then it goes to 3, to 2, right? But it still remains positive velocity
So what would it have to look like for it to go back?
at all times. Great question, Ty.
Would it not have to go to like negative?
Draw a velocity time graph with a similar shape that does show the object moving backwards. Go ahead. Try and draw a velocity time graph with the same shape, that sort of, up and down and up.
This is for all classes.
Okay, you need to draw it, and then I'll show you the answer. What do you need, Rich?
Guys, don't worry, I'm sure for all classes.
You're going to draw notes on
I don't think it's a good thing I am still in that.
You don't have any paper.
Oh, I got sticky notes right here.
Oh, God.
Yeah. Yeah.
Oh, damn.
Hey, here's what I'm going to do. I'm going to take this graph right here, and I'm going to copy it, and I'm going to put it here. Okay? So when I say the same shape, I mean like, well, the same shape. But what about it has to be, what's different for it to be going backwards?
Let's go to the negative.
It has to be in the negative. So what should I do, Brett? Where should I start?
Start at 0.
Start at 0?
Go up. Do the opposite. Go up. And then go bring it down.
Don't you always start at 0?
And they mean like this? Okay. Would that be right? When is this one going backwards?
When it passes 0. Or on the x.
In there, right? It's going backwards. That's not what I expected you guys to say. What I was thinking was starting here, this would actually be slowing down, going backwards and slowing down, and then going forward, and then backward, and then forward, right?
You just start at 0.
You could start at 0 too, yeah. You could do this. You could just go like this, right?
I just think it's so full.
Right? When is it going backwards? Only when it's below. When it's below the axis, it's going backwards. Because the velocity is negative.
Okay.
Okay? The velocity is negative. Okay?
So he's literally doing like this, like slowing down, and he's like going backwards.
If I were doing that on the, I'm not going to set it up, but if we were doing it here, but just say, I'll just walk it, right? Let's say the pencil sharpener is 0.
Yeah.
So I'm here, I'm going forward, and I'm doing what thing?
Going back.
Like from about 0 to 3 seconds.
Speeding up.
I'm speeding up, and then at 3 seconds I
Slow down.
slow down, but go backwards or still forward?
Still forward.
Still forwards,
And then
and now I'm at
6.
6 seconds, and now what?
You stop, then you go
And
back.
I turn around so I don't have to go backwards?
Yeah.
Is that okay? Now I'm going backwards, but I'm
Speeding up.
speeding up.
Slow down.
He's so.
Yeah, it's good enough.
Why speeding up?
Yeah,
Why?
because you start at the 0 at 6, and if you go down, you are accelerating.
Yes, what he's saying. Because my velocity at 6 seconds is 0, and then like at 7 seconds I'm actually going about what? Minus 2, right? I'm speeding up, and then when I get to about 8 seconds, I didn't really speed up very much there. I'm speeding up, and then when I get to 8 seconds, I start to slow down, and then I'm actually going,
Fast. Back.
I'm actually going, slowing right down, and then at about 9.2, I'm actually doing what?
Stop.
Going back this way.
Really fast though. Like,
Really
like
fast,
sprint.
yes. Does that make sense?
Right into the board.
If you get that, you guys are well on your way. If you understand what's going on there.
Okay.
It's not easy because you haven't really seen velocity time graphs, right? Okay, seeing as you guys did that so well, I've never done this with a class, I'm going to see if you guys can do it. What do you think the acceleration time graph would look like for the dot? Let me just make it a bit easier for you. Let's just get rid of this.
Alright.
It'd be like,
Okay, I'm just going to make it a bit smaller so I got some more room. This is velocity time, right? What would, now, acceleration time generally can be positive or negative, so I'm going to go like this.
it'd be like an
So what would it look like?
like an
An N?
yeah.
Like that kind of thing, Zane?
Yeah.
Okay? What would it look like? Well, remember we said that, right? Acceleration, Jeff, stay with me, man. Acceleration graph is a graph of the slope of the velocity time graph. So what is the slope look like? Well, the slope here is it really steep at the start?
Yeah?
Is it really steep right there?
Yeah.
How about we just call that triple positive? Like, it's like 3. We'll say it's 3. Triple positive. And then a little while later, the slope is maybe 2, and then it's 1, and then it's 0. So my acceleration time graph has to go from 3 to 2 to 1 to 0. 3, 2, 1, 0. It has to go like this, doesn't it? To 0. Right? And then what happens to the slope here? Well, now it's -1, -2, -3, and then it goes back to -2, -1, and then back to 0. Right? -1, -2, -3,
Team Brindle coming clutch.
back to 0, and then the slope is 1, 2, 3, 4, 5. Absolutely. How close was Zane? He's pretty close, right? He's pretty close, like this. This acceleration time graph is the same as this, right? Or it's the corresponding one. That's kind of a grade 12 skill. I do a little bit of it here. That's a challenging one to do. I don't usually show that to grade 11s. I know. It's the first time I've ever done that. Okay, so that's pretty good. I'm impressed. Okay. Note that the slope of the curve is not always positive. I've kind of gone ahead here already. I've kind of jumped ahead, right?
See, sometimes why doesn't it?
Yeah, notice that the slope of the curve is not always positive. What does that mean? Between points A and B, Sarah and Jordan, between points A and B, the change in the velocity is -2 cool. Right? Because here at A, it's 4, and here at B, it's 2. And so delta V, the change in velocity, Brandon, how much does the velocity change? It goes from 4 to 2.
2 minus 2.
-2. How much time elapsed? 4 to 5 to 6 to 7, right? And so my change in time from 7 to 4, that's 3. And so the slope is minus 0.67 meters per second squared. The slope between A and B, right? Because really you're just finding the slope here. It's an application of grade 10 math. You're finding the slope down to over 3. The slope is minus 0.67. Okay? What does the minus acceleration mean? It means the velocity is, in this case, slowing down, right? What about this meters per second squared nonsense? Brett was asking about that earlier. Oh, like, what is it? It's not nonsense. Something you maybe haven't seen. It's the unit, that's right. Okay, here's the part that always blows the grade 11's mind. Hang with me for about 3 more minutes, okay? Just hang with me. Let me explain. Don't freak out. I get kids freaking out at this point sometimes. Probably because I've given them so much information. Notice the units on the acceleration. They are meters per second squared. Now, acceleration is the rate of change of the velocity, and velocity is the rate of change of displacement. So I could say acceleration is the rate of change of the rate of change of displacement. I know it's complicated. Don't freak out. Stay with me. In other words, relax. I know I hear this every time. Relax. Acceleration is, now what I really should do is I should have, still making sense? I'm going to cover that up. I'm going to cover that up so you don't freak out so much. Okay. So, would you agree that A is equal to delta V over delta T? We've already established that, right? Acceleration is the change in velocity over the change of time. But delta V is what? How do you find velocity? Distance over time. So I'm going to replace that delta V with d over t, but that's all over t. So I get delta d over t over t. That's just formula. There's no math there.
It's all equal.
Yeah, there's no arithmetic, I mean. Now, if you use the units, and again, please refrain from freaking out. I'm going to make this bigger.
No. Take it out.
Okay, if you use units, Mr. Friesen, who you guys don't know because he's been retired for long enough, that used to do this. It's called dimensional analysis or unit analysis. You take the same concept, but put the units in, see what happens. And we've done a little bit of this. You just haven't been told that you're doing it. Distance is measured in meters. Time is measured in seconds, and then this time is also measured in seconds. So all I've done here is change it to units, right? Okay, now I'm going to rewrite that. Hang with me. Meters per second, I'm going to rewrite that as meters per second, and then this divide by is going to be written with that kind of, right? So this line here is the divide by, and it's divide by seconds, right? Now, you know from about grade 7 or 8 that if you have a fraction that doesn't have a bottom to it, it's really just over 1, right? So it's meters per second divide by seconds over 1. That's a 1. Okay? How do you divide fractions? Do you remember? Flip and multiply. Mervin remembers. Which one do we flip, Mervin? The right one, right? So I'm going to take my meters per second, and I'm going to multiply by, flip, 1 over s. And how do you multiply fractions, Cole? Do you remember? You do not cross multiply as multiplying. You multiply straight across. So meters times 1 is going to be meters, and seconds times seconds, seconds squared.
Yeah.
And that's where the unit for acceleration comes in. Meters per second squared. 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 Meters per second squared. Not meters. You don't know how many times on this upcoming physics test when people write acceleration they put meters per second. And I circle it and I put a 2 in there to get a stamp. Meters per second squared.
It's the same thing
For acceleration.
it's the same thing for acceleration
When it's negative? Yes. Yes.
No, when you use the S, like 2 meters per second.
Yeah. 2 meters per second squared.
It's the same thing.
Same thing. Challenge question for you.
Oh no.
Meters per second is velocity. Meters per second is velocity. Oh, I was just going to ask that question. You're such a jerk, Hassel.
No, it's a square.
Squared. Meters per second cubed. The jerk. Awesome. You guys did really good. I think that's the best time I've ever, that's my best lesson doing that. I'm usually wore out. Most people just kind of tune out during this, but I think I managed to do that today. Okay. I'm going to stop there because I've poured enough into your brains. If you want to take a few minutes and sort of put together your cheat sheet or whatever, remember the test is tomorrow. None of this will be on the test. None of this, just that stuff I showed you at the start. On Friday, we'll talk about Galileo.